Over the last decade, we've seen leaps and bounds in terms of the technology applied to our modern crop of aftermarket fuel injectors. What we're seeing is larger and larger injectors that can still flow incredibly small amounts of fuel, which is vital in order to get good quality idle, as well as cruise conditions or control over our air-fuel ratio at cruise conditions. Traditionally, as we go larger in the injector flow capacity, while the injector can flow more fuel, which is important at high RPM and high boost, where these larger injectors tend to fall over is that their control of very small quantities of fuel at very small pulse widths can suffer. So that's where we get problems with our air-fuel ratio control. The modern crop of Bosch EV14 style injectors has really improved technology here. There's a number of manufacturers providing injectors based around the Bosch EV6 injector, including this one here, which is an ID1050X injector from Injector Dynamics. And these injectors go up to 1700 cc's, with larger injectors coming out. That's all well and good for most modified street cars, but when we're starting to build drag cars, particularly high boost drag cars running on methanol fuel, a 1700 cc injector still is likely to be insufficient. One of the problems is here that obviously as we increase the boost pressure and our target for engine power increases, we need to provide more fuel. But with a lot of our cars now running on alternative fuel such as E85 or even methanol, the amount of fuel or mass of fuel that we need to provide in order to keep the engine happy and get good control over our air-fuel ratio also increases. As a rough guide, when we move from pump gas through to E85, we need to provide around about 35 to 40% more fuel. When we go to methanol, we need to provide somewhere around about 2 to 2.5 times the amount of fuel. So as you can see, this has a serious impact on the injectors that we fit to the engine. Now, when we fit larger injectors, and some of these injectors available in the aftermarket, such as the billet atomizer, now go up to 500 pounds per hour, which is approximately a little over 5,000 cc's or 5 litres of fuel per minute. It's actually slightly higher than that, but just as a rough conversion there. That's a massive injector, so it's more than capable of keeping the engine happy under high boost and high RPM. But again, we get to this situation, trying to make the engine idle happily on a 5,000 cc per cylinder injector, or 5,000 cc per minute injector can be problematic. One of the technologies that has been around for a long time, which we can apply to help fix this, is staged injection, where we have 2 or more injectors per cylinder. There's a couple of ways we can run this. Now, we've seen this a lot in the older naturally aspirated race car development, where 2 injectors are used per runner. Now, this is traditionally not used in order to provide more fuel volume, because with naturally aspirated engines, typically we can easily buy injectors that are big enough to support the engine's power requirements. But these are used in a different way with the staged injection. What happens here is that one set of injectors will be fitted down near the inlet port, near the intake valve. So these spray directly on the intake valve, and this is used at idle and low RPM. Then there'll be a second set of injectors that are placed outside of the intake trumpet, sometimes completely out of the trumpet itself. And these wouldn't work very well at idle and at low engine speeds where the air speed is quite low. However, at high RPM, particularly 7,000-8,000 RPM and above at wide open throttle, using these injectors that are fitted outside of the inlet trumpets can actually provide a small but real advantage in terms of power. This comes through better atomization and mixing of the fuel, giving a more homogeneous fuel air charge entering the cylinder. So staged injection is used here, where the injectors down by the intake port, down by the intake valve, are used at low RPM and low throttle settings. As the driver increases the RPM and throttle settings, the staging moves the injection out to the outboard injectors. In most instances, at high RPM and wide open throttle, all of the fuel would be delivered solely through the outboard injectors. So that's one technique. The other technique which we see more often used in our high boost turbocharged engines is where the staged injection is there to provide more overall fuel flow. Here we'd run on one set of injectors at low RPM and low load where the fuel demands aren't that high. As the RPM and the boost pressure increases, we'll gradually start staging in the secondary injectors so that we're using basically an equal pulse width or duty cycle at high RPM and high boost between both injectors, making sure that we're maximizing the flow through both injectors. Now, the injector size doesn't need to be the same here either. The injectors can be different sizes, and quite often a small-ish injector will be used for the primary injector with a much larger secondary injector, maybe somewhere in the region of 1,000cc primary injector and maybe those 5,000cc per minute secondary injectors. Now, the staging here obviously is quite important in order to get good control over the air-fuel ratio, and I want to just show you how this is done. Every software has its own options. We're going to have a quick look at how Adaptronic handle this in their modular series of ECU. So let's take a look at this. This is actually the map for our Mazda FD RX-7, and the RX-7, the 13B engine, is in stock form uses staged injection because the fuel demands are quite high. We've only got 2 rotors, so if we only ran 1 injector per rotor housing, we'd only have 2 injectors. Really difficult to supply all of the fuel requirements through 1 injector. So we're running a set of ID 1300cc primaries with a set of ID 1700cc secondaries. Here we're looking at our main fuel map. So this is it shown graphically here, and below we've got it numerically. This is a 3-dimensional VE table. We've got RPM on our x-axis and we've got manifold pressure on our vertical axis. So nothing particularly unusual here, and this is a proper VE based fuel model. So the numbers in that fuel table are engine volumetric efficiency. Now let's have a look over at our injector staging. So we'll have a look at our injector staging here, and we can set up the number of stages. So in this instance, being that it is only running 2 injectors per rotor, we've got 2 stages of injection. This particular ECU will support 3 or 4 stages of injection depending how much fuel you actually need to get into the engine. The next option we've got here is a minimum off time for our stage 1 injectors. Now, that might not make too much sense, but essentially what we're doing is telling the ECU that the injector must be switched off for a minimum of, in this case, 2 milliseconds before it can be switched on. And this is all part of the Adaptronic strategy where the stage injection is actually seamless and automated if we want to run both injectors as hard as we possibly can. So essentially what this does is limits the maximum duty cycle that the injector, the primary injector, will operate at. And the way the Adaptronic strategy works is it will run the primary injector up to that limit, and then once we reach that limit, it will bring in the secondary injector and hold that primary injector at that minimum 2 milliseconds off time, and it'll bring in the secondary injector as it needs in order to fulfill the engine's fuel requirements. A big part of this strategy working properly is giving the ECU good data about the injectors. It needs to know exactly what injectors are fitted, so let's take a look at that. We'll come over to our outputs and injector type, and this is where we can define the injectors that are fitted to the engine. Our primary injectors here, as I mentioned, we've got a set of Injector Dynamics ID 1300 cc's. And it's important that the ECU has good data here. It wasn't that long ago that all of the data the ECU really needed was a flow rate as well as an injector offset or dead time table for the injector. These days ECUs are getting a little bit more sophisticated. They've taken after the way OE manufacturers are characterizing the injectors, and they'll also include details such as a short pulse width adder, so they're properly characterizing the injector flow right through the pulse width range that we're going to be applying to the injector. The better the data we can provide for our ECU, the more accurate that control. And with a single set of injectors, if we've got some errors there, that may not be a big deal because we kind of bake in those errors into our VE table. With staged injection, if we want seamless integration when we switch from primary to secondary, It's really critical that this data is accurate. In this case, the Adaptronic ECU makes this really easy. We can just choose our injector from a fairly significant list in a drop-down menu of all of the injectors that Adaptronic have already done the hard work for us and have characterized. So obviously in this case, ID 1300, we don't need to make any changes there. If we click on our secondary injector, this of course defines the secondary injector, exactly the same principle here. And you can see that this has been set up as an ID 1700. So in this instance, there's really no more work for us to do. As I mentioned, the system is automatic and it will just run the primary injector up to our limit and then bring in the secondary. But maybe that's not what we want to do. It's okay, we've got some more control options there. If we go back to our fuel tuning and we come across to our two-stage injection map, we'll bring up this table here. Now we've got a table at the moment that's filled with zeros, and this is because we're letting the Adaptronic do the heavy lifting and decide on the split between primary and secondary injectors on its own. However, we've got a three-dimensional table here. We've got our manifold pressure on our vertical axis, RPM on our horizontal, just like our main VE table. Numbers of 0 here mean that all of the fuel, where possible, will be provided through the primary injector. If we were running a naturally aspirated engine, as I mentioned earlier, where we wanted to take advantage of potentially better atomization and slightly improved combustion, more homogeneous combustion charge from those outboard injectors at high RPM, what we could do at high RPM, obviously we'd only be going up to 100 kPa here, maybe from 5,500 RPM and above, we could set our values in this table to 100%. Now, we're not necessarily going to just put in a big step like this, and instead, as the RPM and the throttle position or manifold pressure increases, we'll gradually stage those secondaries in and get to a point where above, in this case, 5,500 RPM, we're 100% using those secondary injectors. So a lot of control there as to how we use the secondary injectors. As I've mentioned though, Adaptronic there, automated, not every ECU does this. One of the keys when we are tuning staged injection is to do some data logging while we're dialing in the staged injection. And what we want to keep in mind or keep our eye on there is the injector duty cycle or pulse widths of either way for the primary and the secondary injectors. We want to make sure that we're keeping control over our maximum injector duty cycle for our primary injectors. So generally, I like to keep my maximum injector duty cycle at or below about 85 to 90%. So once we're starting to get there, we're going to take note of whereabouts we are in terms of our injector staging map, our load and our RPM, and start bringing in the secondary injectors. The other issue we can run into is if we start bringing in the secondary injectors too early and we're trying to drive them at too low a pulse width, we can also get into some problems there with good control. Most aftermarket ECUs with staged injection will have some kind of limiting factor on what pulse width the secondaries need to be above before they'll come in, but that is a consideration. You get all of this right when you do a dyno run or a wide open throttle acceleration pull on the road or the racetrack. The lambda trace is going to be perfect, completely seamless as we cross over and start staging in those secondary injectors. If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.